Okay, thank you. It's a pleasure to be here, and I'd like to thank Barbara and Guillaume for the invitation. What I'm going to talk about today follows on from Patrick's talk and actually from John's talk, which will follow me, really looking at how we can link observations of seismic anisotropy, a particular seismic attribute, with mineral physics and geodynamics, and I'll sort of show you both a forward and inverse approach to putting some constraints on this. Obviously, not all this work's my own, and in fact, I guess I started this line of inquiry over a decade ago, but most recently James Wookie's really been leading it, and he's got a European Research Council grant that's funding that, the Comitac project. But there's a group of researchers at the University of Bristol in England, and we're also collaborating with Alessandro Forte from the University of Quebec at Montreal. Okay, so we've heard a little bit about the lower mantle already, and I guess the point I'd like to make is really that D double prime is playing a really fundamental role in the dynamics of the mantle and the core, and it's really, it's a thermal boundary layer, so it's the lower mantle analog of the lithosphere. It's the site where plumes are formed most probably, and it's also the potential resting place for slabs. And just as we see regional variations in the lithosphere, oceans and continents, we see similar size regional variations in the lowermost mantle. So, for example, large, low shear velocity provinces could be thought of as an analog in some ways to continents on the surface. And the other really important thing is just as the lithosphere, that the oceans and mountains play a fundamental role in affecting the atmosphere, D double prime, or the lowermost mantle, is serving as a boundary condition for core dynamics, so potentially affects things like the Earth's magnetic field and the style of core convection. In terms of mineralogy, on the right is a model of a pyrolytic mantle, and on the lower part is the Morb equivalent. And the most dominant mineral really in most of the lower mantle is perovskite. But then in the lowermost few hundred kilometers, it's been suggested that there's a phase transition to post-perovskite. And some might argue that this is really one of the most exciting discoveries in mineral physics in the last 25 years. In both models, both compositions, there's a calcium perovskite element. Then in the pyrolytic mantle, there's a ferropericles constituting about 20%. In the more Morb-like mantle, where there's more aluminum, calcium, and other things, you get stishovite and a columbite type phase. But really, what I'm going to concentrate really on in this talk is this transition from perovskite to post-perovskite, and really concentrate on the properties of post-perovskite. So there's been quite a number of papers talking about this phase transition. On the right, I'm sort of showing a particular pressure versus a temperature plot showing the transition from perovskite to post-perovskite. And what's kind of a tantalizing or exciting element of this discovery is that if you're in a very warm mantle, which is shown on the far right there, you may not go through this phase transition at all. Whereas if you're in a much colder mantle, you may enter this phase transition from perovskite to post-perovskite, and then near the very base of the mantle, you may indeed go back to a perovskite phase. And so, as I said, this presents the exciting possibility that we may have a probe for lower mantle temperature. If we just look at different elasticity calculations, I won't really go into details of how they're calculated. As a seismologist, I take this as the output, and I use this in models. On the far right, I've shown two plots of seismic velocities based on two calculations of elastic constants for perovskite. On the left, those are P-wave upper hemisphere projections. So a vertically propagating P-wave would be at the center of this sphere, and a horizontally propagating would be at the edge. And as Patrick pointed out, perovskite has an orthorhombic symmetry, and you can see that the fastest P-wave directions are along the X2 axis, the slowest along the X1. On the right, it's a bit more complicated, and what we're showing is the separation between the two shear waves that propagate independently in an anisotropic medium. And the little tick marks show the polarization of the leading or the fast shear wave. And again, you can see that there's a clear fourfold symmetry And whilst there's some differences, the orientation of the fast shear wave and the relative sense of magnitudes are in reasonable agreement with each other. In contrast, if we go to post-perovskite, there's a lot more variability. Some people's calculations predict very high amounts of anisotropy, others pick lower. Again, it's a orthorhombic symmetry, but it actually, probably to first order, could be approximated as having a hexagonal symmetry. So again, if we look on the left, you can see the variation in p-wave velocities in the left column on the right side. And then on the far right, you can see the variations in the difference between the fast and the slow shear wave. And in contrast to perovskite, there's quite a bit of variability. If you look at a vertically propagating wave, for example, on the top two, the leading or the fast shear wave is polarized left to right, whereas in the bottom one, it's polarized up and down the page. So still some disagreement between different calculations. And as was pointed out in the previous talk, when you get enough of a polycrystalline material and you start to deform it, you'll start to get alignment. And basically the deformation can be accommodated through a number of different mechanisms. You can have diffusion mechanisms at play, dislocation mechanisms, dynamic recrystallization, and grain boundary migration. And in practice, there'll probably be some interplay between these effects, with one perhaps dominating in one regime and the other. The most effective way at orienting or generating a crystal-preferred orientation or a lattice-preferred orientation is the dislocation mechanism. But it's difficult to assess, especially in the lowermost mantle, because we have competing effects of things like temperature, grain size, stress and strain rates, pressures, and then the presence of fluids also. And really, I think some of the big questions are, what are the polymineralic effects? How do things like MgO and perovskite or post-perovskite interact? What are the role of inherited textures? Mantle material will probably have a texture when it hits the lower mantle. And to really understand this, we need to know the slip systems of the minerals that we're looking at. So for our work, we've just taken from the literature, it's probably a bit out of date already, what we think are the ideas of slip systems in post-perovskite. And so, for example, we've taken results that are derived from in situ deformation in a diamond anvil cell, and then results based on density functional theory modeling, and then finally results from large volume deformation experiments. That's on analog, so on the bottom row are the dominant slip systems for the calcium iridate analog, and you can see in two of the predictions they predict an 010 dominant slip system. In fact, on all three in the bottom predict that. Whereas if we look at the actual post-perovskite phase, there's some discrepancy between the different calculations. So really what we're going to do as a seismologist is see which one of these slip systems best fits the data that we record. Before going on to that, though, it's also worth pointing out that there are other mechanisms that are quite effective at causing anisotropy, and really one of the big challenges is untangling one mechanism from the other. So it's been known for a long time that if you have layers of contrasting elastic properties, that's very effective at generating anisotropy. You can also get this from the alignment of inclusions that could be higher or lower in seismic velocity. But a very effective way of generating anisotropy is by having inclusions of melt. And this could be basaltic melt or perhaps even inclusions of core material. And again, we may have some combination of effects at play, which is what we think is happening, for example, in rifting environments in the uppermost mantle. So our probe of lower mantle anisotropy is shear wave splitting. And just as a quick summary, basically if you have an incident shear wave in an isotropic medium, when it impinges on an anisotropic medium, it splits into two independently propagating shear waves. These will separate in time depending on the magnitude of the anisotropy and the path length through the anisotropic region. But this is going to be very directionally dependent, which I showed you in some of those previous slides. You get quite a different result for vertically propagating waves than more horizontally propagating waves. Just to give you an idea of sort of relative magnitudes, these are these spherical plots show variations in shear wave splitting, again with the fast shear wave polarizations indicated on them. On the left is a prediction for a candidate post-perovskite with a shear in the horizontal direction. It predicts a maximum of 3% shear wave splitting. If we look at the case where we've got aligned inclusions of melt that are in tubular cylindrical inclusions, we get much lower amounts of shear wave splitting, much lower amounts of anisotropy. And then the far right, if we have aligned sheets of tabular inclusions of melt, it's very effective at generating anisotropy, in this particular model up to 5%. So it gives you an idea of the types of things you can test. Perhaps the simplest style of anisotropy to look at is known as vertical transverse isotropy. So this is a hexagonal symmetry with a vertical symmetry axis. You can get this from simple layering of materials or horizontally aligned inclusions. And we can probe this by the far right phase diagram shows how you can look at SSCS phases transiting through this region, or even SCS phases at shorter distances. And the model predicts a nice simple separation between the radial and the transverse component. It's because the PSV and the SH systems decouple in this very particular case of anisotropy. And on the far right is an example that sort of shows a very nice separation between the horizontally polarized shear wave and the vertically polarized shear wave. And for a while, that was sort of the best we could do. Two groups have actually taken observations of the onset of the horizontal and the radial component and inverted for maps of anisotropy as a function of depth, so VTI anisotropy. So in both, you can see that there's some clear regional variations, and in the areas of paleosubduction, in areas that are higher in average seismic velocity, the SH phase leads the SV, and then as you move into the warmer regions, the lower seismic velocity areas, you get the opposite effect, where SV is actually faster than SH. So what we've done is tried to pull apart the waveforms a bit better and actually look at what we call source-side shear wave splitting analysis to really constrain the anisotropy to D double prime region, but also invert for a more general form of anisotropy. This gets difficult because we know the uppermost mantle and in both the area of the receiver and the source are most probably anisotropic. So one has to account for that first, and one has to apply the splitting operators very carefully. They're not commutative in their operation. So what we compare is the anisotropy accrued at the receiver and the source by looking at a lower mantle turning S phase that turns above the D double prime region. And then we use that to diagnose the contribution to the shear wave splitting and the SCS phase that comes from the D double prime region. And this is an attractive approach because as data coverage is improving, we're starting to get more and more crossing ray paths in the lowermost mantle. So here's a particular plot looking at events from the Northwest Pacific recorded in Europe, and then Hindu Kush events recorded in Canada. And these ray paths cross at the core mantle boundary below northern Siberia. So really, once we start getting crossing ray paths, we're starting to sample more of that upper hemisphere projection of the two shear waves, or the shear wave splitting, and we can start to pull apart the mechanism. For example, distinguish hexagonal mechanisms from orthorhombic mechanisms if we have enough coverage. So the approach is it's one of these calculations that's actually really quite easy to do, but it's also really easy to do incorrectly. So we have a series of checks that we impose on the analysis. So we have to have a very simple receiver anisotropy. We don't want multi-layers or dipping layers, that sort of thing. We try to use similar azimuths for both the S and the SKS signals. We only keep the best quality measurements, one with low error, a very clear signal, and that requires clear signal on multiple phases. And then finally, one of the things you get out of the splitting analysis is what the initial shear wave polarization was, and that should agree with what we think we know about the source mechanism. So the initial source polarization must agree with the CMT solution for that earthquake. And so in areas like North America, where there's really a proliferation of stations, it now presents really exciting opportunities to map the more general form of anisotropy underneath this region. So you can see that the coverage is shown on the right. Geometrically, it gets a little bit complicated. It's usually the type of thing you do wrong the first time. But we've been able to use a lot of ridge events, which has really opened up a lot of the coverage in this region. And so here's very quickly a summary of the results for this area. We see a quite steeply dipping fabric. In the southernmost region, the little bar and tick mark with the 52 and the 15 degrees, the degree of dip on the structure. This is just inverting for a tilted transversely isotropic structure. But then as you move up into the northwest, it rotates, and the orientation of the anisotropy rotates in azimuth, and the dip becomes shallower. And we have some confidence in this because we've got a lot of different rays crossing from different source receiver paths. And really, putting things together, this is kind of the current picture that we have. In the areas in yellow where there's a little tick mark, or in blue where there's a tick mark, we have an idea of what the orientation of the general anisotropy is. In the blue areas without a tick mark, these are areas where all we can say is SH is faster than SV. And then the areas that have got multicolors in them, there's a lot of uncertainty, different results, different experiments suggest different orientations. And it's also worth pointing out that there are some areas that appear to be isotropic. So for example, region 8 underneath the Atlantic doesn't seem to show any evidence of anisotropy. So what are the next steps? So essentially what we do is and we can do this for any mineral, but we test post-perovskite as a causative mechanism for the anisotropy. We use current best knowledge of the elasticity and slip systems for post-perovskite. We try to use state-of-the-art models of Mantle flow, which incorporate chemistry. So Nathan talked about that in the first talk. Ideally, we want to consider strain history in 3 dimensions. And ideally, we want to impose no restriction in the style of anisotropy. And this is the approach that we've tried to take. So on the far right, it shows a snapshot of the flow model from the work of Simmons and Forte and others, showing the flow directions. The white bubbles are the particles that we traced. We follow the strain history along these particles, and you can see they're moving in 3 dimensions. From that, we do a viscoplastic self-consistent calculation of the lattice preferred orientation of the post-perovskite, and that allows us to predict a texture. That's a pole figure up in the upper right of the orientation of the A-axis of post-perovskite. Then we do a Voigt-Roos-Hill averaging to get the elastic constants, and once we've got that, we can build a seismically anisotropic model that we can ray trace through. And then the final step is to compare those predictions to the observations. So I won't go into this in too much detail. This is published in a paper by Andrew Walker and co-workers. Essentially, as I said, we choose a point, latitude and longitude, where we'd like to know what the elastic constants are, and then we back project along the particle trajectories using a numerical integration, and then we do a viscoplastic calculation along each one of those points. So on the far right shows, and we start this when we enter the post-perovskite region, and we finish when we leave it. And you can see a whole selection. This is just a 2D projection of a whole selection of trajectory paths through the D double prime region. Then we then consider the 3 sort of reported slip systems. One is 010 as a dominant slip system. The other is 100. And the final one's 001. And these are the different slip system activation energies that are plotted there. Infinity just means that can't be activated. So as I said, we take the viscoplastic self-consistent calculation gives us the pole figure, which is up in the upper right. So this tells us an orientation of the crystal, both in azimuth and inclination. And we can then accrue, we can then look at the single crystal elastic constants, which are estimated from those results I mentioned earlier. And then we do a Voigt-Roos-Hill average to come up with the effective elasticity at a particular point along a particular trajectory path. And that's what's shown in the far right. Then once we've done that and covered our region of the lowermost mantle, we can then accrue what the measured shear wave splitting would be. Okay, so to date, we're just using a ray theoretical synthetic of shear wave splitting. We basically just add the splitting operator as you move along the ray path. And so it's you end up with a series of splitting parameters. One of the assumptions in this is that the splitting time is smaller than the dominant period of the seismic wave. So that sort of summarizes going from the flow models to predicting what the shear wave splitting would be. And really what's more interesting in a sense is going from what the observations are to saying something about either the mineral physics or the flow. And obviously this is still work in progress, but we're looking at shear wave splitting observations. We may impose some limit on the symmetry and the style of anisotropy that we have depending on how the analysis was done. That then gives us some idea of orientation. We then invoke some assumptions about rheology and the way material responds to shear, which allows us to infer something about a shear direction. And then there's the other big assumption of what is the response of shear to flow and strain history, and then that in turn can hopefully tell us something about flow. So here's sort of a summary of our most recent results. We're comparing observations of general forms of anisotropy at the base of the mantle, underneath the Northwest Pacific on the left here. In the middle, these are the results for the Caribbean, and on the far right, the results for the area below Siberia. What's shown in these plots is just the flow 200 kilometers above the core mantle boundary as predicted from one of Nathan's models. Then we see how well the VTI tomography models, which slip system best fits those results, and then we look at which slip systems best fit the most general form of anisotropy. So in the upper right, a somewhat confusing a diagram. It shows a chi-squared misfit between the observations and the predictions, and this is a circular misfit, not a linear misfit. And it only really looks at the orientation of the shear wave splitting. It doesn't say anything about the magnitude. And we compare in the top how well the 100 dominant slip system fits versus the 010 versus the 001. There's a histogram in the background there in blue, and where that's darkest is where, if you just do a random simulation, the result you get. So as you can see, is a random simulation from the slip systems that doesn't really, it does just as good a job as comparing to the observations, with the exception of the P010. So to within 1 sigma, that dominant slip system is standing out as fitting the data better than the other two slip systems. So as I said, it's a bit preliminary, but it provides a framework for doing this sort of analysis to say something about deformation and slip systems in the lowermost mantle. So conclusion, so obviously in general the lowermost mantle is anisotropic, but there's very clear regional variations, which is good. It means it's going to tell us something interesting about the nature of the lowermost mantle. And I would argue that the anisotropy really is the fingerprint of D double prime mineralogy and the style of deformation. We've compared observations with numerical predictions from link flow and LPO modeling, and 3 different plasticity cases for dislocation creep in post-perovskite are considered. And given the state of where we're at right now, the 010 slip system is the one that seems to fit the data the best. In terms of future directions, well, obviously there's going to be a lot more observations that can be made. There's bigger data sets. I think full waveform modeling, finite frequency effects are going to be really important. It's not really for us to solve, but I think there's some real open questions about the role of dynamic recrystallization, work hardening, and then finally the presence of other phases. For example, if we start considering the interaction of MgO and perovskite or post-perovskite. Something I've been interested in a long time is just what are the effects of inherited petrofabric textures? Does when perovskite goes to post-perovskite, does it lose all its fabric, or does it inherit something? Effects of melt. Melt could explain all the observations we're looking at. We can't rule out preferentially aligned inclusions of melt at this stage. And is LPO and post-perovskite important everywhere in D double prime, and do other anisotropy generating processes play a role? So I'll just leave with a picture of what we're working on right now. PhD student Jack Walpole at Bristol is looking at more global data sets. As you can see, we're never going to do a great job in the southern hemisphere. On the left, on the lower left, is the number of hits in azimuthal bins, so very good coverage through most of the northern hemisphere. But probably what's more important is the azimuthal coverage. And you can see that that's a bit more patchy, but where it's sort of warmer colors, you've got very good azimuthal coverage, so you should be able to untangle the style of anisotropy a lot more accurately. So I'll stop there and take questions. Thank you.